Hi kids, we'll be talking about how to calculate electric field in some situations. Before that let me explain some situation and let me use it further. So there is a situation here where there is a hemispherical container in the sense obviously closed container, and I am filling it with a gas of which is exerting a pressure P. Now I'll be drawing the free body diagram of the gas and the container. So anyway, let me look at the force exerted by the gas on the container. Gas will be pushing the container, right? Now similarly container will be pushing the gas, exactly opposite direction. Now if I want to find what is the net force because of this yellow things, by symmetry I can see it should be in this direction, but if I want to calculate I have to take components and I have to integrate, but I can easily show you that should be equals to the force exerted by this green color stuff, because gas is in equilibrium. When it is in container it will be in equilibrium. So from now onwards I am going to say whenever there is a constant pressure force acting on any random shape, if I can close the other surface with a lid, I am going to say that force is going to be pressure times of that area of the lid. We call that as effective area sometimes. So if I want to find the force exerted on this surface, I can simply say it is P into pi r square. P into pi r square, pressure times of effective area. Now I will be using this further to calculate what is the field due to hemispherical shell. So if there is hemispherical shell of charge density sigma, and if I want to find the field here, what I will do is I am going to put a unit charge there, and I am going to say force exerted by this hemispherical shell on that unit charge is nothing but field. So the other way of saying it is that will be same as force exerted by unit charge on the hemispherical shell. So we need to find what is the force by the shell on the charge, but we are going to find what is the force by the charge on the shell. So for that I will be taking a patch on the shell and I will find what is the force on the shell. For that I need to find the field first, that is K1 by r square, that is field due to this charge, into the charge of the patch. Charge of the patch is sigma dA. This is the force on the patch and it is perpendicular to the area, perpendicular to surface. Now this is the force, and if I divide with the area, it looks like constant for any guy on the surface. So that is like a constant pressure. Pressure times of area will be force. It looks like constant pressure. Just now we have seen when it looks like constant pressure, we can go with pressure times of effective area. Pressure times of effective area. Effective area is the lid area, which is pi r square. When I substitute K is 1 by 4 pi epsilon naught, I am going to end up with this answer, right? Now once we see this, we can easily take this analogy to surface tension also. Now I am going to take this frame, which is semicircle, line, line and line. I am going to take this frame and I am going to dip it in soap solution and I am going to take it out. Then soap film will be formed. Now I am going to draw the free body diagram of soap film separately and frame separately. Now on the soap film, this frame will be pulling the soap film in this direction, right? Now this soap film will be pulled by the frame in this direction also. Now this is easy to calculate obviously. If there is one interface, it is T times of 2R, because this is 2R diameter. But there are two interfaces, so 2 times of T into 2R. Anyway, the two interfaces has no much role for us. So the other way of saying it is, I can say the force due to this yellow stuff is nothing but force due to this white green stuff, which is T into 2R. If one interface, two interfaces 2 times. See, I didn't draw the horizontal forces because they will be getting cancelled anyway. So from now onwards, when it looks like this, I can go with effective length. Not only this shape, it can be any random shape also. If I can close those 2 points by a straight line, then I will go with that effective length. We will see how we are going to apply it for a ring. Now I want to find what is the field due to half ring here, which is nothing but if I put a unit charge here, what is the force exerted by half ring on the unit charge, which is same as force exerted by the unit charge on the half ring. Now I am going to find what is the force exerted by unit charge on the half ring. So I am going to take some element and I am going to find the force on that element. Force on that element will be field there into charge of that element. Now that is in perpendicular to the length, you can see. Now that is force on this length. If I divide with this length, then I am going to get force per unit length. This is force per unit length. It looks constant for every element. It looks like surface tension, which is constant for every element. Once you see it is force per unit length which is constant like surface tension, I can go with surface tension times effective length. Effective length is 2R. Surface tension times effective length. K value, yeah, this you can see R and R will go 2K lambda by R. 2K lambda by R. Field due to half ring. Field due to half ring will be 2K lambda by R, which is exactly same as field due to infinite line charge. We will see why it is. If there is a line charge here, only line charge is there. This circle I have drawn for my reference. If there is a line charge of charge density lambda, and if you want to find the field here at a distance R, which is not symmetrical situation. Now we will take one element, we will find the field and we will integrate. So let me do the same thing. So at an angle theta, I am going to take some element and I want to find the field due to this element here. So where this angle is theta and this length is r, I can, by taking this triangle, I can show you this length is r tan theta and this length is r secant theta. So if this is y, this has to be dy. So differentiation of this is this much. So the length of this element is this much. Once we know this, then we will straightforward calculate the field there. That is going to be k into charge of this element by distance square. Secant square will go. This one will look like this. Just for easy understanding, I am going to write this one like this. I am going to multiply and divide with r. Why I am going to write this is so that I can show you it looks like k into q by r square. Now, if I want to explain, you look at this circular arc. At an angle theta, when I take small angle d theta, such that length is r d theta. So basically, I have taken circular arc or ring, and I am taking some small element on the ring, which is of same charge density as line. Then charge on this one will be lambda r d theta. Field due to this one here is k into charge on that thing by r square. So essentially what we got, field due to this element here is same as field due to this element here. So from there we concluded field due to this element and this element here will be same, given that this charge density and this charge density are same. Now once we understand this, whenever there is a rod like this, you can replace it with a circular arc like this, because every element is covered. Now suppose this line is infinite line charge. This angles will become 90, then this is going to become half ring. So field due to infinite line charge and half ring are same, we can see that. Now going to the other kind, if I want to find the field due to square plate of uniform charge density sigma at a distance d by 2, where side length is d. So what I will do is I will put a unit charge and I want to find the force on the unit charge. So force on the unit charge is same as force by the unit charge on the plate. We are going to find force by the unit charge on the plate. So for that I will put a unit charge here. I will take small area. I will find the force. That force will be in this direction. But by symmetry, the net force should be only in this direction. So in this direction, the force will be charge there into electric field. Charge there is sigma into dA. So sigma dA into E will be the force, but I need only this component, that is along area vector. So charge is sigma dA into electric field there, cos theta component. I need only that and I have to integrate that. That cos theta component I can write it as E bar dot dA bar. Sigma dA is the charge, into E is the force, but I need only cos theta component. So dA into E into cos theta will come together. I can write it as dA bar dot E bar. This one I can modify and I can write it this way. This is nothing but flux. And so basically we want to find what is the flux due to this unit charge in this square plate. For that we will construct a cube and we can easily show flux through that is 1 by 6 epsilon naught. Charge is unit charge, so 1 by 6 epsilon naught. Right? So that is the field due to, basically that's the force on the plate by a unit charge, which is nothing but force by the plate on the unit charge, which is nothing but field due to the plate. And going to the other kind, this, there is a ring. If you want to find the field here, we will find the potential first. That is easy to find, and distance of every element is same, which is root of r square plus x square. So potential here will be this much. Now if I want to find the field along x axis, I will be moving it slightly along x axis and I will be seeing how the potential is varying. So basically if I want to find the electric field along x axis, I will be doing this thing, differentiation of this, then you are going to get this answer. Now electric field along x axis we got, and by symmetry we can easily see electric field along x axis is the only thing which is surviving. So I can say this is the total electric field, right? Thank you.